When you think of cast iron, you probably picture something heavy, strong, maybe a little old-fashioned. But what if I told you that simple material has a secret life? It's a shapeshifter. It can be engineered to have wildly different personalities. And today, we're going to pull back the curtain and see exactly how that happens. So here is the central mystery we're going to solve. How can you take two pieces of iron with almost the exact same chemical recipe and have them turn out as complete opposites? I mean, one is tough, easy to work with, and the other is as hard as glass and will shatter if you look at it wrong. The answer is pretty amazing, and it all comes down to a choice the iron makes in just a fraction of a second. Let's meet the two main characters in our story. On one side, we have our hero, gray iron. It's machinable and it's tough. Why? Because its carbon takes the form of soft, flaky graphite. But on the other side, we have the villain, white iron. This stuff is incredibly hard and brittle because all its carbon is locked up tight in a nasty compound called cementite. Same base ingredients, two totally different results. So, as that molten iron starts to cool down, it reaches this critical decision point, a literal fork in the road. It has to decide what it's going to do with all its extra carbon. And believe me, the path it takes determines everything about its final personality. Okay, so option number one is what we call the stable path. This is the easy way out, you know? It's the low-energy, preferred route. If the iron takes this path, the carbon precipitates out as pure graphite. You can think of it as the iron just relaxing and letting the carbon form its own soft, lubricating structures. This is what gives us our tough, machinable gray iron. But there's another path, the metastable path. This is what happens when the iron gets trapped in a higher energy state. It's rushed. Instead of forming that nice soft graphite, the carbon is forced into a chemical marriage with the iron atoms, creating a whole new, super hard compound, iron carbide, or what we call cementite. And this stuff is the source of all that hardness and brittleness in white iron. And you can literally see the result of taking that good path right here. You get these desirable graphite structures. Sometimes they look like flakes, sometimes they're compacted, and you can even get perfect little spheres. This is what gives cast iron its amazing versatility. The alternative? A brittle network of that hard, unforgiving cementite. The difference is just night and day. So this is the big question, right? What's the guide at this fork in the road? What's nudging the iron to choose the good path over the bad one? Well, the main answer, the master puppeteer pulling the strings in this whole process, is silicone. Now, foundries are not just guessing. They have this incredibly powerful tool called the carbon equivalent, or CE for short. Think of it like a tendency score for the iron's recipe. This formula combines the effects of carbon, silicon, and a few other things into one single number. A higher score, which you get by adding more silicon, means the iron is much, much more likely to take that nice, stable path to graphite. But here's the thing, the recipe isn't the whole story. What really matters is what you end up with. Modern foundries use a technique called thermal analysis to actually listen to the iron as it solidifies. It's incredible. By monitoring the heat it gives off, they can see in real time which path it's taking. The recipe is the starting point, but the final structure is everything. Okay, so we've got our guide, silicon, telling the iron which way to go. But what happens if the iron is in a huge hurry? What if it's cooled down so fast that it doesn't have time to follow the directions? Well, this introduces our next crucial factor, time, or more specifically, the cooling rate. Just take a look at this graph. As the cooling rate gets faster along the bottom, notice what happens to the transformation temperature on the left. It drops. The faster you cool the iron, the less time it has to make that right choice. You force it to solidify at a lower temperature, and that heavily favors the formation of that hard, brittle cementite, even if you had the perfect amount of silicon to start with. And this brings us to a really key concept in foundries, chilling tendency. It's basically a measure of how likely an iron is to panic and get forced down that bad, metastable path when you cool it too fast. A high chilling tendency is a huge red flag. It means you're at high risk of making brittle parts, especially in the thin sections of a casting that always cool down the quickest. But here's the thing. This doesn't sound very predictable, does it? But it is. This is not a random process. Foundries are absolute masters of controlling this delicate dance between chemistry and cooling. They do not leave this to chance. They engineer the outcome they want, every single time. So how do they do it? Well, it's a four-step process. First, they dial in that base chemistry, getting the carbon equivalent just right. Second,
They add what are called inoculants. These are tiny little particles that act like seeds, giving the graphite a perfect place to start growing. Third, they carefully control the cooling rate through some really clever mold design. And finally, they verify everything with that thermal analysis we talked about, making sure the iron is behaving exactly as planned.
And the result of all that control is the ability to create these incredibly complex, high-performance parts, like this engine block. Every single property of this part, from its strength to how easily you can machine it, is a direct result of meticulously controlling that fork in the road while it was solidifying. It's really a symphony of materials science in action.
So, if you take one thing away from this, let it be this. The incredible properties of modern cast iron are no accident. They are the result of pure engineering, of deliberately pushing a material to the very edge of two different states, and then controlling which path it takes with incredible precision. It's all about controlled instability.
So, the next time you see a piece of cast iron, remember its properties weren't just determined by a simple list of ingredients. They were engineered. The real question isn't what's in it. The real question is, what did we ask it to become? And that right there is the power of modern materials science.